Okay, a couple things before we get too deep into it. So I mentioned that Excel certification thing. So the more I got looking into it, they only gave me kind of a free code for me and not for multiple users. So I'll get a link on or an announcement on Canvas that has that information, but that is going to cost something. I'll also put a link to the one that I know is on Google for any of those that were interested in that after I mentioned that. But there, I couldn't figure out exactly how much it was without trying to kind of actually pay it. So I'm not sure how much that would cost. I thought it was free, or they gave me codes to multiple students, but that wasn't the case. The more I looked into it, so I just got excited. But I probably should have waited to mention it until I looked more into that. But also. So on the syllabus, it says that like the exam's supposed to be, I think, this Friday. We're not ready for that. We kind of pushed the other one a little bit forward. So I'm going to kind of do this similar thing with this one. I think we're still in a good place, and we'll be able to cover the material we need to for the final. So I'm thinking probably next week we'll continue to do hypothesis testing, and then the exam will be early the following week, right? So I'll have a little more information about the exact dates and then kind of times. But probably kind of early, not next week, but the following week. Oh, okay. All right. So that being said, any other questions for me? I'm going to X out this so I don't have any more pings before we get going here. Okay. So we're going to jump into this thing called hypothesis testing, which is going to kind of come from a similar point that confidence intervals did. So with confidence intervals, we didn't know where the true mean was. We didn't know where the true population proportion was. Same kind of idea with hypothesis testing, but we're going to be able to develop some statistics that are a little more useful than what we have with confidence intervals. So we don't know where this population mean is, so we're going to develop what we call a null and alternative hypothesis about where it lies. Okay? So when I say null and alternative hypothesis, the null hypothesis is what we're going to assume to be true. So this might be something like, I don't know what the average income in the U.S. is, but I'm going to assume it's $50,000. That might be my null hypothesis. So the alternative hypothesis would just be the complement of that. So if I say, maybe I think that the average income in the U.S. is greater than or equal to 50,000, the alternative would be that it's less than 50,000. Okay. So I might go out, take a sample mean, I find a sample mean of, 45,000. Well, that goes against my null. That goes against what I assume to be true. But we know that the distribution of sample means will be centered around 50, that assumed true value of 50,000. But we could see, values slightly to the left and slightly to the right. So is 45,000 sufficient enough evidence to be able to reject it? That's kind of the ultimate question we want to be able to answer. Maybe I assume the average income is equal to 50,000. If I saw a sample mean of 90, well, that seems like it's far enough away that what I assume to be true probably isn't true. Right? But if I saw 46, 52, those are kind of really close to 50,000, and I know that I'm not going to see 50,000 from every sample mean, even if the true mean is 50,000. Right? So if we have sufficient enough evidence like that example I gave where we saw it was 90,000, well, then I can reject the null. What I assume to be true probably isn't. Okay? If I don't have sufficient enough evidence, then I would fail to reject the null. Okay? Just some kind of a motivating example. So what we're going to be kind of using today is this idea that maybe I want to test the assertion that the average mass market beer has a lower ABV than this Bell's Two Hearted, which is 7%. Right? So I'm wanting to test for whether or not the kind of average mass market beer has a lower ABV than 7%. So what we're going to do with a null and alternative hypothesis is whatever you want to test for, that's your alternative hypothesis. And then you'll stack the deck against yourself by assuming the opposite is true. So here I want to see, is the ABV for the average mass market beer less than 7%? So I assume the opposite is true, which is that it's greater than or equal to 7%. Okay? So I could take a sample, I see 4.5. Well, that goes against my assumption. My assumed true value is that it was greater than or equal to 7%. but does it go against it enough, right? Is that far enough away from that 7% cutoff that I can reject that null? So that's the ultimate question we want to answer. So before we get too deep into it, how do we kind of construct, and what are some things we need to know about the null and alternative hypothesis? So we'll write the null hypothesis as H subscript 0, right? And this is going to be what we assume to be true, or kind of the true state of nature. The alternative hypothesis, we'll write H subscript A, and this is like essentially the complement of the null, right? Or it's the exact opposite, the contradiction to the null. So if I assume that the average income is greater than or equal to 50,000, the alternative would be that it's less than 50,000, right? So it shouldn't be anything too terribly tough there. So we've got this null, we've got this alternative. What we're going to do is be able to figure out, okay, I've assumed that the true mean is somewhere in this range. I then take a sample. If that sample is inconsistent with what I assume to be true or inconsistent with that null, well, then I can reject the null, right? So let's say I assume that the average income is equal to 50,000, sorry, greater than or equal to 50,000. I find a sample mean value of, I don't know, let's say 30,000. Well, maybe that's inconsistent enough with that null of being greater than or equal to 50,000 that I can reject it, right? I could also find evidence that supports, right, or it's not inconsistent with the null. So maybe I find a sample mean of 60,000. Well, that is greater than or equal to 50,000, so that supports the null. So of course, if it supports the null, then I'm not going to reject that null. But maybe I find a sample mean of 49,000, which is inconsistent enough, but it's not strong enough evidence to be able to reject that assumed true mean of being greater than or equal to 50,000. So those are kind of the three scenarios we have. Either the evidence is consistent with the null, so we don't reject it, or it's inconsistent with the null, in which case we have two scenarios. Is it so inconsistent that we can reject the null, or is it not very inconsistent and we actually would, don't have enough evidence to be able to reject the null? And those are kind of our three scenarios. I think I want to go through this and then we'll kind of dive into some other .cam here. So the analogy that we can kind of make to a court case with this null alternative hypothesis, I think a good way to think about it is, if you're going to a court case, what are you really trying to test? You're really trying to find if that person is guilty, right? So what do we do? Well, what should we be doing in the justice system is we assume the opposite is true. We want to find whether or not this person's guilty. So our null hypothesis is that we assume that they're innocent, right? So the null hypothesis here is you assume they're innocent, which means the alternative is that they're guilty. Okay? Then if you find enough evidence, right? So maybe you're looking at, I don't know, a murder case and you find their DNA and they had a motive and there's no alibi, right? So you find that you have sufficient enough evidence that goes against that null, right? You go to jail, right? They reject the null. If you got enough evidence that goes against you being innocent, then they reject you as being innocent, and then they, now you're guilty and you go to jail. But if you don't have enough evidence that goes against the null, right? Maybe there's no, DNA evidence at the scene of the crime. You have no motive. You just didn't have an alibi. Well, okay, there's not enough evidence that can go against that null, and so we kind of remain to think that null, we fail to reject it. You leave and we assume you're still innocent. Okay. Yeah, I don't know. I thought that was funny at one point in time. So let's. This is my one-tail, two-tail stuff, right? Let's go into a little bit of a discussion about what we're doing with this hypothesis test. Switch over to the .cam here. So using that one example as kind of a motivation, before we get too deep into different types of tests, let's say we wanted to test for whether or not that average mass market beer has a population mean that's less than 7, right? So the alternative hypothesis is what we want to test for, which means the null is just the exact opposite so that it's greater than or equal to 7%. That's kind of the idea of what we're doing. Well, I know that if I take samples of size 36, I think it was the number that we had, I think n was 36, that meets the central limit theorem, so my sample means should be normally distributed around whatever the true population mean is. Okay? Well, now the problem is I can't observe what that true population mean is. Right? But what I do have is I've assumed it's greater than or equal to 7%. Okay? So anytime we have this null and alternative hypothesis, the way that we'll kind of set these up and the more discussion we have about it, I think it'll be clear as to why. And I'll revisit this idea later on in the class. But we're going to just use kind of whatever that cutoff value in that range is, right? So if I assume that the mean is greater than or equal to 7%, well, I'm just going to use that 7% as the assumed true mean, in which case I know that if this in fact was the true mean, my sample mean should be normally distributed around it, right? So I then go out and I find a sample mean of 4.5. Right? Well, I can figure out how likely it was for me to see that value of 4.5 if this was in fact the true mean, right? Because the probability that I saw 4.5 or anything below it, well, I can turn that 4.5 into a z-value, right? It's just that before we had kind of this equation, the only thing that's going to change is I now don't have the population mean, but I'm using the assumed true population mean. That's the only thing that changes. Okay? So once I find, turn this into a z-score, I could look that up and find the area to the left. Right? So what that would tell me is how unlikely it was, right? The probability that I saw something this far away from the assumed true mean or anything further away. Now, the issue is, if this is pretty low, right? So let's say that I end up turning this into a z-score and I don't know, I see that the probability is like 0.001 or something, right? Well, if I end up finding a probability that's really, really low, what's probably true is this isn't the true mean, right? Because it would have been so unlikely for me to see 4.5 if in fact the true mean was 7, right? Probability I saw 4.5 was 0.001. So it's probably more likely that the distribution of my means is actually, I don't know, maybe I'll make up a number here, centered around some value that's lower, right? And now seeing 4.5, well now, that would be a very likely, right? The probability of seeing it 4.5, if this was the true mean, would be very likely. Okay? So if I see something that's inconsistent with that assumed true value, potentially I can reject it and say, well, look, it's probably that the probability I saw 4.5 was so low, it's probably that this isn't the true mean and that the true mean is actually something lower. Okay? But how do I determine if my sample mean is inconsistent enough with what I assume to be true in order to reject it, right? Like, how low does this probability have to get before I can reject the null? So that's kind of, that's kind of the idea of like where we're kind of going. We're just kind of giving a better idea of what we're doing with hypothesis testing. So we'll talk a few more specifics, right? The example I just had set up was the example of a less than test, right? So we have 3 different types of tests. This one, notice my alternative hypothesis has a less than sign in it. So we're going to call that a less than or a left-tailed test. If my alternative hypothesis instead had a greater than sign in it, we're going to call that a greater than or a right-tailed test. Now notice this mu0 here. I kind of wrote that earlier and I forgot to mention. Mu0 is just this idea that, right, this is the assumed true mean. It's coming from the null hypothesis. It's the assumed true mean. So in practice, this ends up being a value, right? Mu 0 ends up being here, it was 7. And then we have kind of the third, which is a not equal to test, right? So notice all of these tests are named after the alternative hypothesis. Greater than test, less than test, not equal to test. Right? So the name of the test or the type of the test you can get by looking at the alternative hypothesis. Some other words that we'll use for this, greater than, we'll sometimes say greater than or, oh. You guys gotta let me know that you were able to see that. Hold on. Sorry. I forget the first time I always have to switch back over. So what I was just mentioning was we have 3 different types of tests, right? The one that we were looking at here was that less than, so left tail test. Mu 0, so we have here as being 7%, right? That's our assumed true value. And these tests are named after the alternative hypothesis, right? Greater than, less than, not equal to test, okay? Another kind of word or terms we'll use here is greater than we'll call a right tail test, less than, left tail test, and not equal to we'll call a two-tail test or two-sided. So here we've got our one-sided test, and here's our two-sided test. So why are these kind of one-sided? Well, if you think about it, what evidence for this greater than test would go against the null or support the alternative? Well, only values that are above the assumed true mean, which would be, if it's above the assumed true mean, it's a to the right, or a right-tailed test. For a less than test, what's the only evidence that goes against the null or supports the alternative? Those would be values that are below the assumed true mean or on the left tail. But what about for a two-tailed test? Well, for a two-tailed test or a not equal to test, if I'm assuming that that true mean is equal to a certain value, then I could actually see a sample mean below or above, and both of them would go against that null hypothesis, right? Let's say I assume that the true population mean is equal to 7%. Well, then seeing 4.5 or 9.5 are both sample mean values that go against that null, right? Both sides or both tails matter here, right? We have a two-sided test. Okay. Any questions on kind of anything here or the notation or? Okay. So these steps are, I'll mention them. It's kind of intuitive, but first we have to figure out, are we looking for a population mean or population proportion? That's really easy. Once we identify the null and alternative hypothesis, we have to determine whether or not we have a one or a two-tailed test. By the end of the class, we'll kind of see our first reason as to why that matters. And then also, just to be like complete, we want to make sure we have an equality sign somewhere in the null and alternative hypothesis. So notice, kind of the normal convention is to always include it in the null hypothesis. So it makes sense with a two-sided test. I'm going to have the equality in the null because that is what I'm saying. It's equal to a certain value. For a left-tailed and a right-tailed test, we'll just always include the equality in that null hypothesis. Now, we'll eventually see it doesn't matter if I kind of put it in the alternative because the probability of any one value for a continuous distribution is 0. Right? But the normal convention is to include that equality sign in your null hypothesis. Okay? So let's kind of return to our example. Right? So what's our null and alternative hypothesis? Well, I kind of already gave this to you. Right? I jumped ahead a little bit. Right? We said if we want to test for whether or not the average mass market beer has a lower ABV than 7%, well, that was saying is that, the true mean less than 7, that's what I want to test for. That's my alternative hypothesis. So I assumed the opposite is true as my null, which is that it's in fact greater than or equal to 7%. And you kind of can think about here how you would say it in words. The average mass market beer is lower than 7%, or here the complement of that would be that it's not lower, that it's greater than or equal to, which is kind of what we have written in kind of statistical form here. So here, what type of tailed test do we have? we base it off the alternative hypothesis, I've got a less than sign in the alternative hypothesis. So it's a less than or a left-tailed test, because only values that are less than 7% or in that left side go against the null or support the alternative. Okay. So let's go through another example. What if I wanted to find, an economist wants to establish that the mean retirement age is different than 67, right? So here, the alternative hypothesis, what I'm testing for, is that that mean retirement age is different than the value of 67, which is really just saying that it's not equal to 67, right? Anything other than 67. So we assume the opposite is true, which is that it is in fact equal to 67. Okay? And these two-tailed tests will work a little bit differently, so we'll get to that in a little bit. But here, if I see a mean retirement age of 71 or 63, those both go against that assumed true mean of 67. Then the question becomes, well, are they inconsistent enough that I can reject that as the true value? Okay. We're going to skip over this. If we have time, we'll kind of come back to this, or otherwise we'll kind of pick up with this on Monday because we don't have class. I'm canceling classes Friday to kind of keep my sections at the same level. So you guys get a study day on Friday this week as well for this class. So we're going to skip through type 1, type 2 errors. We'll think a little bit more about these kind of after we get through the next discussion. So where do I want to pick up? I think it's right here. Yeah, there we go. So kind of this idea is that, okay, if I assume that it's equal to 7% and I see 4.5, is that inconsistent enough that I can reject 7% as the assumed true mean? That can't be correct, right? That my assumption has to be wrong. Well, I talked about, we could find test statistics and things like that. So let's go through that process a little more formally. So if we've got this assumed true value in the null hypothesis, we're going to have two approaches in which we can figure out, okay, what sample mean would be inconsistent enough with my null that I can reject it. So the one we're going to talk about today is the p-value approach, and then I think Monday we'll probably pick up on the critical value approach. Okay? So this p-value approach is what we're going to look at today. So we start out with our example. Right? We've got our null alternative hypothesis. Now, I want to mention here, I'm writing the alternative hypothesis here as H subscript 1 because some of the problems in your Connect homeworks, or if you're looking at the book, might write it that way, or even if you're looking at outside sources. I mean, for me, I'm just like, it makes more sense to write H subscript A, and we don't have to use just numbers. If you talk to like a guy in the stats department, he probably is like used to writing things like this. But I think for us, it makes a little more sense. Yeah, sometimes we'll see H subscript 1 as the alternative, but on the exams, things like that, I'll write it as H subscript A. Just a little bit easier to identify what we're looking at there. Okay. So I've got a left-tailed test, right? Less than sign in the alternative hypothesis. Right? Well, if that assumed true value or that assumption in the null hypothesis is true, so that the true mean is greater than or equal to 7%, and I have a distribution, and I have a sample size of 36, what does the distribution of my sample means look like? Well, I kind of already alluded to what that would be. It would kind of be this blue distribution here, right? But I want to give a little bit more insight. So you can kind of ignore this green distribution for now. Let's say I find the probability that I saw something that was that far below the assumed true mean or anything below it, right? So I'm kind of thinking about this probability down here. If instead, right, here's my null hypothesis. So why did I use 7? Why didn't I use another value in this range? Why didn't I use 8% as my assumed true mean? Well, the reason why is because if I think about if this was my assumed true mean, my distribution would be normally distributed around that value. Well, now seeing 4.5 is even more unlikely. Notice here, I mean, you can barely even shade the area in here. So if before the probability was 0.001, using the assumed true value of 7, if I use any other value in this range of the null hypothesis, the probability I saw that sample mean is just going to go down, right? So if I can reject 7%, well, I for sure can reject any value above it. So that's why we kind of use this cutoff value as the assumed true mean. Okay? Any questions on that? Hopefully that makes sense. Why we're kind of choosing the lowest value in this range here. Okay? So we already said then, okay, we'll use that 7%. Then the distribution of my sample means, and I kind of write sample means here as what's on your x-axis. Well, I could see 4.5, I could see 6.7, 8.5. Well, here, 8.5 and 9.5, those values support my null hypothesis. So if I saw 8.5 or 9.5, well, geez, I'm for sure not going to reject my null. I just found evidence that supports it, right? So those are easy ones. Well, what about 4.5 and 6.7? Well, look, 6.7, I mean, how unlikely would it be that I see 6.7 if the true mean was 7%? Well, it depends on the standard deviation, right? We've talked with other examples in the past. Like, yeah, it's only 0.3 away, but if my standard deviation is only 0.1, well, that's 3 standard deviations away. So we can't really say until we know what the standard deviation of these sample means are, right? Which, if we recall, right, this standard deviation of my sample means, we use this in confidence intervals, right, was just the square root of the variance, population variance, over my sample size. So once again, we're going to start out with our hypothesis testing examples where we don't know the population mean, right? That's the whole reason we're doing these hypothesis tests. We're ruling out certain values. Excuse me. But we somehow know the population variance. These will be weird situations. It's more likely that we only have the sample variance, but we're going to start out assuming we know the population variance and then talk about what changes if we have the sample variance, similar to how we work through confidence intervals. So, you know, how likely or unlikely is 6.5 and 5.5%? Where are we at in time? Okay. So we see that 4.5, right? It goes against the null, but does it go against the null enough? Right? So this is where we need to start talking about how do we actually conduct this hypothesis test. So what we're going to do is turn that sample mean value we found, so turn that 4.5 into a z-value, okay? How do we do that? Well, we subtract the assumed true mean and divide by that standard deviation of my sample means. Because we're using an assumed true mean instead of the actual population mean, we're going to call kind of this z-value a z-statistic, right? So more broadly, this is a test statistic. It's just identifying this is a test statistic that comes from a standard normal or distribution or the kind of z tables. So this z statistic is really just a z value. It's just referencing that we didn't use the true population mean, we used an assumed true population mean. So there's our equation, right? Where we can relate before, you know, if I wanted to, similar to confidence intervals, I could calculate intermediate steps here because what does this denominator represent? That denominator, notice, is this guy here. That denominator represents the standard deviation of my sample means, right? Just to be clear, I drew this arrow because the standard deviation of my sample means is equal to that. So I could, you know, calculate this first and then plug it in, or I can just do it all at one time. So once I have that z value, we're now thinking about, oh, I just lost the marker. This is my z statistic, okay? All right, so we hopefully already know what all these things are. Here, the assumed true mean was kind of our, you know, came from our null and alternative hypothesis. So this p-value approach, what we're going to do is use that z statistic to find the probability Did I saw a sample mean as far away from the assumed true value as I did, or anything further away that goes against the null? So, before we get too deep onto that slide, all right, we'll use the same setup. I saw the sample mean of 4.5. So what I'm thinking about is how unlikely was it, or how likely was it, that I saw 4.5 as my sample mean if in fact this assumed true mean of 7% is the true value? Well, if this was in fact the true value, the probability I saw something that was that far away from the assumed true value, or something even further, is kind of the area under the curve and to the left of that 4.5. Well, now that we have our z-statistic equation, which is really just the same thing that we were doing for turning a sample mean into a z-value, once I find that z-statistic, I can look that up in the table, and the table tells me the area to the left. Right? So what's the probability that I saw something this many standard deviations below that assumed true mean, right? Because now our z-statistic, it's the number of standard deviations not below the true population mean, but below the assumed true population mean. Okay? So what's the probability I saw something this many standard deviations below that assumed true mean, or anything even further away? Okay? If this probability, let's say we look it up, and I don't know, it's 0.03. Okay? So this area, this represents my p-value. The probability I saw something this many standard deviations away from the assumed true mean, or even further. Okay? Now, if that probability starts to get really low, well, then I'm probably going to be thinking, yeah, it's probably that this isn't the true mean. It's probably that maybe like this 5.1, some value lower is, because then it'd be a lot more likely I saw this 4.5. Right? But what probability is too low? Like what probability, how low, at what point is the probability I saw something this far away from the assumed true mean low enough to where I'm okay rejecting it? So what we're going to do is we're going to set this thing called kind of alpha. Right? And this relates to type 1, type 2 errors, which we skipped for today, but we'll revisit that on Tuesday. We'll kind of come back to that. I kind of think I don't know why I set them up in that order. I like going through the topic in this order a little bit better. So alpha is essentially saying, well, look, I'm going to set my alpha at 0.05. So what this is saying is, look, if I see a sample mean such that the probability I saw that sample mean, or anything below it, given the assumed true mean, if the probability falls below 5%, probability falls below 0.05, or less than a 5% chance that I saw that value, well, then I'm okay rejecting it, right? So I'm setting that threshold for like, what probability is too low? Here, I've said 0.05, anything below 0.05, right? So really, whether or not we can reject the null hypothesis is based off this rule of, is the p-value less than that alpha that I selected? And I choose alpha. Well, for the problems you guys work through, you're probably told what alpha is, but in practice, like, we can choose different alphas, okay? We can start to think about, it's probably going to be kind of like confidence intervals. If I set an alpha of 0.05, and I end up being able to reject it, what I'm really saying is I can reject this null hypothesis with 95% confidence. Or if alpha is 0.1, 90% confidence. 0.01, 99. So it's very similar to confidence intervals. So here's kind of my rule, right? I reject that p-value is less than alpha. Now, everything I have here is for a left-tailed test. This was our kind of original example, right? This left-tailed test. So the probability that we saw 4.5 or something lower, this isn't the actual p-value, right? We didn't turn it into a test statistic or a z-statistic yet, but assume it was 0.03. Well, then we say, okay, that's a low enough probability, right? It's lower than that threshold of alpha I set, so I'm okay rejecting that, right? It's likely that this isn't the true value. So, another term that I'll start using, another way I'm trying to tell you what the probability actually represents, but another way of thinking about it is the p-value is the probability that you saw the test statistic that you did or anything more extreme, right? Now, why didn't I say anything less than that? Because what if we had a greater than or a right-tailed test? Okay. So if we had a greater than or a right-tailed test, and here I'll use a different example, some different numbers so we can kind of think about. So let's say I've got, maybe I assume that, oh wait, I don't want a right-tailed test. So greater than 7, so that now the null is less than or equal to, right? So I'm basically just running the exact opposite test. But maybe I don't see here, right? Like, so I got the same kind of setup, but instead of seeing 4.5, which would actually support the null now under this test, let's say I see, I don't know, 8.5, right, as my sample mean value. And here, right, that was just my assumed true mean of 7%. Well, now, another way of thinking about this is the p-value is the probability I saw the test statistic that I did, which once I have the population variance, I could determine what that standard deviation, I could turn this into a z-statistic. It's the probability I see this test statistic, but not anything less. Now for a right-tailed test, it's the probability I see this test statistic or anything greater or anything to the right, right? So that's why, we can't just use less than or greater than, because it's really the probability to see this test statistic or anything more extreme. This test statistic or anything more extreme, right? Another way to interpret, so now my p-value, right, for a right-tailed test is over here. And in practice, once I have this test statistic, I go to my standard normal table. It tells me the area to the left. I would then have to do 1 minus to get the area to the right. But these are all kind of old principles we already, hopefully we're getting real comfortable using that standard normal distribution to find the areas to the left or right of certain values. Okay. Another way to think about this p-value, and this will help us once we move to this idea of two-tailed tests. So the p-value is the probability that I saw something that went against my null hypothesis this much, right? So the probability I saw something that far away from the assumed true mean that goes against the null, or anything that would go against the null even more, right? Because every value in this range would go against this assumption that it's less than or equal to 7%, even more than 8.5 would, right? And so that's just another way of thinking about that p-value as well. Okay. Any questions up to this point? Okay. So let's dive into what if I've got, let's say I assume that it's exactly equal to 7%, right? So now I've got my two-tailed test, okay? So for a two-tailed test, things are going to work a little bit differently, right? So I've got assumed true value of 7%, and let's say we just keep using that value of that sample mean value of 4.5 that we did earlier. So I might think about, okay, here's my p-value, right? The probability I saw something that went against that assumed true value, or something that went against that assumed true value even more. Right? So I turn this into a test statistic or my z-statistic. I can look up and find the area to the left. Cool, I'm done. I found my p-value, right? It's in this area in the tail. The issue with a two-tailed test is seeing a sample mean of 4.5 it would have been equally as likely, if this was the true mean, it would have been equally as likely for me to see a value of, not 8.5, 9.5, right? Something that was 2.5 above that mean. And now the probability of seeing something that goes against the null hypothesis as much as the sample mean that I did, or anything that goes against it even more, well, now every value on this side has a counterpart that goes against the null just as much on the other side of the distribution, right? Because 4, which is 3 away from the mean, or 10, which is also 3 away from the mean, now both go against that null, because the null is that it's equal to one value. So both sides of the distribution now, we have values that would go against that null hypothesis. Whereas before, if I saw, for a right-tailed test, if I think about, okay, what's the probability I see something that goes against the null this much or anything even more? Well, now if I think about the other side of the distribution, something that's 1.5 below, so 5.5, well, that actually supports the null, right? So the p-value is the probability that you see something that goes against the null as much as, you know, what you saw from your sample, or anything that goes against it even more. And for a two-tailed test, just because I only see one side of the, you know, I see a sample mean that's on one side of the distribution, it would have been equally as likely for me to see anything on the other side of the distribution as well, and all those values would have went against the null for a two-tailed test. Okay. So my p-value is really the total area in my tails here, which really means that each side has half my p-value. Okay. So in practice, I'm only seeing one sample mean and finding one test statistic. So in practice, what I'm going to do is, okay, I see that test statistic, but I know it's a two-tailed test. So once I find this area, I'll then multiply it by 2, right? Because I know it's only half. So when you go to the slides, that's what this is saying down here. Because sometimes you'll see a positive test statistic, sometimes you'll see a negative test statistic. So in this scenario, I would have found a negative test statistic. I saw sample mean below the assumed true value. So I would have found the area to the left of it and multiplied by 2. If instead I had seen a positive sample, let's say I saw a sample mean of 9.5, and I ended up with a positive test statistic, well, now I'm going to find the area to the right of that test statistic and multiply it by 2. Right? That's all that slide's saying. Honestly, if it's just easier to think about, you're always looking for kind of plot your test statistic and look for the area in the tail, right? More extreme. And the only difference is that when you have a two-tailed test, all right, you got to multiply it by 2. Okay. I see something coming on the chat. No? Okay. Any questions up to this point? Now, in all scenarios, right, in all scenarios, once we have that p-value, we then compare it to alpha, and if it's less than alpha, excuse me, we reject. Okay. Any questions on that before we keep moving? All right, where are we at in time? 7 minutes left. Okay, let me think about what I want to do here. Okay, we can walk through this. So here's kind of just a synopsis. I've drawn all this out for you, but here it's all kind of in one place. Left-tailed test, you find your test statistic. Now it's a left-tailed test, so you know the only values that go against the null are things on the left side. So your test statistic for a left-tailed test is usually going to be negative, right? If it's not negative and it's over here, it would actually be a value. Where's this at? If I find something over here for a left-tailed test, well, these are values that supported the null, right? These were values that were greater than or equal to 7. So it wouldn't even make sense conducting a test for something in this range because it supports the null. I know I'm not going to reject the null. Excuse me. But for any value that goes against the null, it's going to be something that would be below that assumed true mean. So we know that for a left-tailed test, negative test statistic, and you're looking for the area to the left of it. for a right-tailed test, right? Well, we should be seeing things that go against the null hypothesis, right? The things that would go against this are only things on the right-hand side or things above the mean. So we know that we should see positive test statistics. Remember, once we turn this into a test statistic, we're using the standard normal distribution where the mean is 0. So now once you find your test statistic, it'll be the area to the right. And then for a two-tailed test, this is where we said, well, look, it kind of depends. We're only going to see one of these, right? But we know that if I see, the negative test statistic, it was equally as likely for me to see something that was that many standard deviations away from the assumed true mean, but on the other side. And both sides, those values that were that many standard deviations away from the assumed true mean would be values that go against the null. Okay? So once I find one of those areas, I just multiply it by 2, and that's my p-value. Okay? Any questions on this? So what are our steps going to be? So we got that rule, first of all. Well, first, determine the null alternative. Hopefully now we can see that it matters if we have a left, right, or a two-tailed test, how we go about this. We're going to be given alpha, or in practice we'll specify it, but for most of the problems you're going to be given this level of alpha. And then you're going to calculate your z statistic, right? So we had an equation for that, which was, let me see if I can find it, and I'll put it up on the screen real quick. Here was our test statistical equation where we said, the intermediate step you could calculate, or you could just plug this in and do it all at one time. Once you have that test statistic, right, we talked about, depending on the type of test you have, which you determine based off the alternative hypothesis. The alternative hypothesis tells you if you have a less than, greater than, or two-tailed test. You'll figure out your p-value, and then the fifth and final step, you compare the p-value to alpha. Okay? If your p-value is less than alpha, you can reject. If it's not, you fail to reject. So let's say we had worked through this one example, and we found the test statistic, and we actually found that, where did I have the one where we compared it? Here we go. Instead of 0.03, maybe I found that this was like 0.13. Well, 0.13 is not less than that alpha of 0.05, so I would say I fail to reject, right? Yeah, this isn't very likely, right? But it's not unlikely enough, right? It's not below that threshold that I set, okay? I'm trying to think if there's anything else I want to say here before we end today. I think that what we'll do is we'll pick up on Monday. We'll use the same example, but I'll give you the population variance. We'll work through it with some actual numbers. We'll go through a couple more examples of hypothesis testing. I'll just keep talking about it and giving you kind of more insights. And basically all next week is just going to be hypothesis testing and getting us kind of ready for that exam the following week, okay? All right. Other than that, no class Friday, so I will see you guys on Monday.